Day 5, we'll start looking at tree diagrams. So the first game that we're going to play as a class is called the Starburst Grab Bag. Here are the rules of the game. The player chooses one starburst from the bag and records the result, and then chooses the second starburst without replacement. So what that means is they'll take the starburst out and keep it out before they take the second one out. The player wins if the two starbursts are matching in color. So we're going to play the game 10 times together as a class and record the results. So for this video, I'll just put what I had doing this game 10 times. So for the first one, the first starburst that I drew was red. Oops. And then the second starburst was yellow. And if they're different, you don't win the game. The second draw, I got red and then red. So that means, yes, I was a winner. The third draw was yellow and then red, and then it was red and then yellow. Then I got a red, 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 yellow, red, red again, yellow, red, 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 and yellow, red. So again, when you have the same color for both draws, you win. So the third game was not a winner, nor the fourth. The fifth game was a winner. The sixth game was not. The seventh was. The eighth game was not. The ninth game was a winner. And the 10th game was not. Okay, so we'll do this in class. We'll probably have some different data. But if we take a look at these 10 games, what is the probability of winning this game? Let's highlight. We got one winner here, 2, 3, and 4. And then probability is what they're asking for out of the total. So the probability that we win this game is 4 out of 10. So we won 4 times out of 10 times total. What information would you need to know to calculate the theoretical probability of winning? So we would have to know how many of each color are in the bag so that we could do the probabilities. So in this particular game, there were 5 red and 2 yellow in the bag. So today we're going to look at building a tree diagram and what are the different parts of a tree diagram, how can we use that to calculate theoretical probability. So we've done the area models where it looks like a times table or an addition table. Another way to look at probability is to draw this tree diagram. So it says fill in the blank boxes with the correct probabilities. So again, this is theoretical. We have 5 red, 2 yellow. So what is the probability that the first starburst that you choose is red? And there's 5 red out of 7 total. So this will be 5 out of 7 for our first draw. The theoretical probability that you get a yellow is 2 out of 7. Okay, now this is called conditional probability because what we did first does affect what we do next. And what that means is we pull out a starburst and we're going to keep it out, and that's going to change our probability on the second draw. So let's say we did get a red on the first draw. What that means is now there's only 4 starbursts left out of 6 total. So the conditional part does change, again, the second probability. And again, if you took that first red one out, there's still 2 yellow, but again out of 6 total. So there's the second draw. So again, conditional probability will change some of our numbers here. Okay, so let's just keep going along this part of the tree diagram. Let's say that, let's see here, first is red. Okay, so now what was our probability that our second one, that we win the first game? So we got the first is red and the second is red. So if we multiply along the branches, so if you think back to what we did yesterday, the counting principle says you multiply together the probabilities. The probability that we get red, red is 5 out of 7 times 4 out of 6. And when you multiply fractions, you just go straight across. So 5 times 4 is 20, and 7 times 6 is 42. And so we have this probability, 20 out of 42, that we win the game. And if you want to calculate the percentage for that, 20 divided by 42, it's about 0.476 or 47.6%. Okay, let's calculate the second probability, which is we get red first, and then we get yellow second. So that would be, again, you multiply. The first probability is 5 out of 7 that you get the red. And then theoretically, we have a 2 in 6 chance of getting the yellow. And so that probability is 10 out of 42. And again, if we want to look at the decimal for that, it's about 23.8% that we get a red first and a yellow second. Okay, now what if we got yellow first? So that is going along this part of the tree diagram. So if we get a yellow first, it does again change the probability in the second draw in that we have 6 left, but there's still all 5 of the red left. So 5 out of 6 that we get a red. And then again, if we got yellow first, there's only 1 yellow left out of 6 for our second draw if we get yellow, yellow. And then again, if we multiply the probabilities together, 2 out of 7 times 5 out of 6. Here's the probability that we get yellow first and red second. Again, 10 out of 42, which is again about 23.8%. And what's the probability that we get yellow, yellow? 2 out of 7, 1 out of 6. If you notice, that didn't happen in our game. We got a bunch of reds in a row, but not yellow, yellow. And that probability, still a winning probability, right? So maybe I'll make this blue here. 2 out of 42. And again, this is a winning game. So was this. This is when you win. 2 colors that are the same in a row. Here's when you win. And that is about 42, about 4.76%. Okay, so there's a few things going on in this tree diagram. The first is we have this conditional probability, which changes the numbers in the second draw. We have dependent events, so I'll write that here. The probability of the second event depends on the first. Okay, so now we can, with this tree diagram, find the theoretical probability of winning the game. We would just add these together. So let's highlight this. We have our 20 out of 42% chance of or 20 out of 42 chance of getting red, red, 4 out of 42 chance of getting yellow, yellow, and we just will add those together. So those are the ending probabilities. So we have our 20 out of 42 of red, red, plus 2 out of 42 yellow, yellow, and that's 22 out of 42. When we add fractions, we keep the denominator the same. We add together the numerator, and that's about 0.52 or 52% chance that will win the game. That's not too bad, right? 52%. So then our last question here, what is the probability that the first starburst was red given that the person won the game? All right, so this is called, again, conditional probability. You might see it written out like this. Probability that the first was red given, they'll draw this line right here, the person was a winner. Okay, so for that one right here, what that means is, what's the probability of a red winner over, and it changes, so conditional probability changes like the outcomes that you're looking at. We're just looking at the winners. So what was the probability that we were a winner? Okay, so this is right here. This is right here. Okay, so the probability of a red winner was the 20 out of 42. divided by the probability that someone was a total winner, which was 22 out of 42. And if we calculate that, we divide out the fractions. I would use parentheses when I'm typing this in right here. That is about 91%. Okay, so if you're looking at just all the winners, what's the probability that they had red, red instead of yellow, yellow? 91% because there were just, there were more red in the game. So that's conditional probability right here, where this thing is given, which changes the total number of outcomes. We were just looking at winners on the bottom here, and that was a 22 out of 42% chance of that. So this is the intro to tree diagrams. There are several things that you should notice. The first is along the split branches, the sum is always 1. So let me kind of highlight what I mean by that. So in our first draw, 5 out of 7 and 2 out of 7, this is 100% of what can happen, right? You either get the red or the yellow, 100% of what can happen. Same thing right here in our next draw. This is 100%. These add to 1. Likewise, these add to 1. And then lastly, our outcome should also add to 1 or 100%. So all of these numbers right here, they add to 100%. This is 100% of what can happen. Okay, so quick notes, a summary of what we saw here. We used a few new terms. One is independent events. The outcome of one event does not change the probability of other events. So it's like the gambler's fallacy that we looked at when you flip the coin. One flip of the coin doesn't affect the outcome of the next flip of the coin. All right, but there are dependent events where the outcome is affected. So when one thing happens, like you pull a starburst out of the bag, it's going to change the probability for the next event if you don't put it back in. Okay, and then the other thing that we looked at here too is along the branches, they should add to 1. So we kind of highlighted that here, and all our outcomes will add up to 1 because it's 100% of what can happen. All right, so let's do an example of a tree diagram. Isaac has a Spotify list with over 1,000 songs. All the songs are classified as either pop or rock, with 40% being pop, 60% being rock. Of the pop songs, 80% of them are short, less than 3 minutes, while only 25% of the rock songs are short. Suppose Isaac uses the shuffle play to choose his first song of the day. Can you construct a tree diagram to model this process? Okay, so first we'll start with all songs. And two things can happen. There's a 40% chance you get pop. There's a 60% chance you get rock. And again, those add up to 100%. Okay, then of the pop songs, 80% of them are short. Which means 20% of them are long, over 3 minutes. Okay, and then same for the rock. For the rock songs, 25% of them are short, which means 75% of them are long. So what are the probabilities of getting like a short pop song? We would multiply along the branches, and that would give us our probability of getting a pop song that is short. So if you multiply those together, that's 0.32. What's the probability that we get a pop song that's long? We'll multiply 0.4 times 0.6, which is 0.8 or 0.08 or 8% chance of getting a long pop song. What's the probability of getting a rock song that is short? So again, we'll multiply 0.6 times 0.25, which is 0.15 or 15% chance of getting a rock song that's short. And then lastly, what's the probability of getting a rock song that's long? Again, we'll multiply those together. 0.6 times 0.75 is 0.45. Okay, describe the meaning of the point 80 in the tree diagram. All right, what that means is, given a song is pop, and this is the 80% we're looking at, there's an 80% chance it is short. Three, what is the probability that a short pop song is chosen? Okay, a short pop song is 32%. Again, you just multiply along the branches. 0.4 times 0.8, 0.32. And again, if you notice, all of these numbers right here add to 100% of what can happen. What is the probability that a short rock song is chosen? So that would be the 15%. All right, find the probability that a short song is chosen. Oh, just short. So we're going to add together the pop short and the rock short. So that's 0.32 plus 0.15 is 0.47, which is 47%. And then here's conditional probability. Given that a selected song is short, what is the probability that it was a pop song? So what's the probability it's a pop song given that it's short? Okay, so what that means is we'll look at how many total were short. And we did that right here. How many short songs are there total? 47%. So that goes on the bottom. And out of those 47% that are short, how many of those short songs are pop? And pop was, the short pop song was a 32%. So that was this right here. So this is that conditional probability here. And we'll divide that out, and you have a 68% chance, given that the song that's selected is short, that it was pop. So we'll take a look at tree diagrams. We'll review more tomorrow on tree diagrams, but your assignment will be on Desmos. So you're going to log into Schoology and click on that link and finish it for tomorrow.